Okay, welcome to the unit oscillations. In this unit, we'll dive a little bit more into the motion of the harmonic oscillator. In the previous units, you have seen that the harmonic oscillator, which is a mass m suspended on the ceiling with a massless spring with spring constant k, is described by a differential equation. This differential equation has the general solution x of t is capital A times sine omega t plus phi. Now, the frequency omega is set by the spring constant and the mass m, but the values of the parameters a and phi are not set yet. And these depend on the specific solutions that we can find when we add boundary conditions on the problem of the harmonic oscillator. These are, for example, the position at the start or the speed at the start. Let's look at a few examples. In the first case, let's assume that we extend this mass downwards to a distance a, and then at time t equals 0, we release it without any speed. So as boundary conditions, we have at time t equals to 0, x is a, and dx dt is 0. Now we can fill it out in our general solution, and we find that x0 is equal to a, capital A, times sine of phi. Now, taking the most simple solution, we can find, we take phi equals to pi over 2, then the sine has its maximum amplitude, and we take capital A equal to small a. In this case, our solution, x of t, is a sine omega t plus pi over 2. And if you know your trigonometry well, you know that this is equal to a cosine omega t. Now let's look at a slightly different boundary condition. So we again extend the mass at time t equals to 0, but we don't release it yet. We wait. We wait until time t equals to capital T over 4, so a quarter of a period. And then we release it without any speed. So again, at t equals to capital T over 4, we have that x is equal to small a, and dx dt is equal to 0. In this case, we can again satisfy our boundary conditions by taking phi equal to 0 and capital A equal to small a. So our general solution is then, for t equal and larger than capital T over 4, a times sine omega t, and for smaller times we get just a. So let's look at how these solutions look in reality. So I just made a few plots here. So case 1 is the solution where we release the mass at time t equals to 0, and we see that it's an oscillating behavior, again, such as a cosine. So it starts at its maximum amplitude and then oscillates back and forth until infinity. Now if we release it at a time t is equal to capital T over 4, essentially we give it a phase lag of pi over 2. And we see that the oscillation is maximum at this phase lag of pi over 2, which is equal then to capital T over 4, and then afterwards it again follows this cosine pattern. But of course this is just a description of a sinusoidal pattern. So now we have seen how this relative phase shift between the two solutions occurs. Essentially it's just a matter of how, at what time we release the mass m from our position where we extend it to. So now let's look a little bit more into the general solution. So let's again focus on our case 1 solution, where we have x of t is a cosine omega t. This is of course a solution that is applicable for every t larger than t equal to 0. So we can also calculate now the speed. The speed is the first derivative of the position. So if we take the first derivative, apply the chain rule to this x, we can find that the velocity is equal to minus a omega sine omega t. Finally, we can also determine the acceleration. This is the second derivative of the position to time, or the derivative of the velocity to time. Our acceleration as a function of time is now minus a omega squared cosine omega t. Again, applying again the chain rule on, for example, the velocity. So how do these look in time. Therefore, we plot them all relative to each other. So at the top you see the position. So at time t equals to 0, we extract the mass m and release it. So it's its maximum extension at time t equals to 0. Then it moves back and forth, and you can see that after one period it goes back into this maximum position. At half a period it's at the opposite side, at its maximum extension. Now what about the velocities? So we have shown that the velocity at time t equals 0 is equal to 0. That's our boundary condition. So we see that the velocity at t equals to 0 is 0, and then the velocity increases and is at its maximum when the position is actually 0. That means the oscillator goes through its equilibrium position. Then the velocity becomes 0 again when the oscillator is at its maximum extension. And finally, of course, the velocity returns back to its maximum when it goes back again through this equilibrium position. Now finally, the acceleration. The acceleration is maximum when we release it, because then the particle is accelerated towards the other side. The acceleration then decreases until it is 0 when the particle or the mass m goes through its equilibrium position. And it is essentially maximum again when it reverses its path, so when it changes its sign from the velocity. And again, also the acceleration oscillates back and forth. So one important part is that if the motion x is harmonic, then also the velocity and the acceleration are harmonic. The velocity is phase shifted with relative respect to the position, and the acceleration is has the same phase as the position, but only inverted. Now, to give you an idea of the value of harmonic oscillations for a wider range of physical problems, you can also consider the motion on a circle. The motion on circles may be something you have seen in the spark, where you have seen the light moving on the bicycle wheel. And you know from your trigonometry that if you have a motion on a circle with radius a, that the x-coordinate is given by a times the cosine of the angle, and the y-coordinate is given by a times the sine of the angle. So now if the angle varies in time, such as for example in the case of this wheel, you can describe the x-coordinate and the y-coordinate by these harmonic oscillating functions, sine and cosine omega t. As another example, you can also think about the pendulum. The pendulum is quite a complicated system, but if you solve for the force equilibrium onto the pendulum under certain boundary conditions, you can show that it has a differential equation that resembles the differential equation of the harmonic oscillator quite closely. In this case, it's not the variable x that is determining the motion of the pendulum, but rather the variable theta. And so the differential equation is the differential equation for theta, but its shape and form is the same as that for a harmonic oscillator, so you will expect also the solutions to be quite the same, only with x replaced by theta. But again, the theta has now a sinusoidal harmonic oscillating pattern. So in summary, in this unit I've shown you that the differential equation solution is dependent on the boundary conditions, and you can calculate the specific solution given certain boundary conditions. I've also shown you that the phase difference describes the relative starting point of the oscillation, and that the speed and acceleration are also harmonic and can be derived from the position of the harmonic oscillator.